Okay, so I want to talk a little bit more about how to do a phase plane analysis, and in particular how to use the information that you actually get from this to tell you about the asymptotic behavior of the function in question. So the behavior as t goes to infinity is usually what we care about. So I want us to look back at our nonlinear drag model. And so we would have an object that's strictly falling, right? So it's dropped from a certain height and it falls toward the ground. With the coordinate system drawn and the force diagram drawn correctly, we can then turn that into a second order equation like we did in class today, and then use this sort of recognizing that this is really a first order equation in disguise, turns it into a first order autonomous nonlinear equation like this. All right, so we want to draw a phase plane for this thing and somehow use that information to tell us how this thing should behave. So the vertical axis is going to be the v prime axis. The horizontal axis is going to be the v axis. So notice that there's no time dependence in the phase plane. All right. Note also that because there's no time dependence in the phase plane, this really only works when your equation is autonomous. All right. If it were non-autonomous, ignoring t dependence would be a bad move, because your equation innately depends, sort of inherently really depends on the value of t in the non-autonomous setting. All right, so autonomous equation, phase planes are good. So we draw our phase plane like this. The vertical axis is the derivative axis. The horizontal axis is the original function v. And now, just viewing v prime as a function of v, we know exactly what this graph is going to look like. All right, this is a squared term. It's quadratic in v, and so this thing's going to be a parabola. This coefficient is positive, so it's going to be an upward facing parabola, dragged down a little bit, no pun intended, dragged down a little bit by this constant negative g. And so negative g is going to be somewhere down here. This thing is an upward facing parabola that looks like this. All right, so what this is really doing for us is it breaks the plane into a few important pieces. All right, so that point right there is important, as is this point right here. All right, these 2 points are where v prime is equal to 0, right? This is exactly where the v prime graph crosses the v prime equals 0 axis, the v axis. Right, and this point also has v prime equal to 0. Okay, now, real quick, if you think about what's going to happen here, if your initial velocity is whatever this v value is that gives you v prime equal to 0, right? So if you imagine your solution has initial velocity that puts you exactly on this dot, then just like we saw in class with the direction field, well, v prime being 0 means that nothing's ever going to change, right? Your velocity is going to be the same forever. And so when you have a point like this in your phase plane, this is usually what you would call a fixed point or a stationary point. Right, and both of these are fixed points for this differential equation. Right, and again, the intuition is that if you had a velocity that started you on that point, it would never be changing because its derivative is 0, and so it would stay there forever. Right, this is kind of the idea. So if you picked the right starting velocity, the right initial velocity, it would never change ever in this model of the physical world. All right. So those are 2 important pieces. The other important pieces are what's happening in between the fixed points and what's happening on either side of the fixed points. All right, so over here, right? So let's look on this region here. Over here, our function, our graph, is strictly above the axis, meaning that v prime is positive here. All right, so let's use a different color. This corresponds to v prime being strictly bigger than 0. And that means that v, as a function, if its derivative is positive, that means that v itself is increasing. And so again, we would draw arrows pointing that way to increase that v is increasing. I'm sorry, to indicate that v is increasing on this region in the phase plane. All right, same idea in between here. our function down here is negative, right? Everywhere down here, v prime is below the v-axis, so v prime is negative down here. And that means that v, as a function, any initial velocity between these two fixed points would lead to v prime being negative, and so v would be decreasing. And so we would draw the arrows pointing in that direction to indicate that it's decreasing. All right, and the last piece is basically the same principle that's happening over here. Right, on this piece of the graph, v prime is positive, which means that everywhere it's positive, v as a function would be increasing, and so we would draw arrows pointing to the right to indicate that it would be increasing. Okay, so from this relatively simple procedure, just looking where things are positive and drawing arrows in the right direction, we can actually talk about some pretty interesting asymptotics for the velocity. Right? In particular, we already said that if you are on this dot, you stay there forever. So let's just think about what would happen. Let's say we want to talk about this dot as a good example. Right? So if you end up on this dot, you stay there forever. So let's say that we start off with an initial velocity that's here. Right? So let's say our initial data says that our initial velocity should be like negative 1 meter per second or something, right? Just some value that corresponds to this dot. Well then, qualitatively, what this sort of flow chart tells us is that our function is going to be decreasing, our velocity will be decreasing forever, just asymptotically approaching this critical velocity here, right? Whatever velocity corresponds to that dot on the axis, our velocity is going to decrease forever, only approaching that velocity but never attaining it, right? That's the idea. So, similar idea, if we started with an initial velocity that's very negative, right? So our initial velocity is down here somewhere, say it's like, I don't know, if this critical velocity is like negative 100 meters per second, let's say that we start with negative 200 meters per second, right? So something very negative. Well, what this model actually says is that this falling object, which is already going really fast, instead of continuing to speed up in the negative direction, it's actually going to slow down. Right? So its velocity is actually going to move back, increase, which as a negative number makes it closer to zero, toward this critical velocity here. All right, so that's really the idea. From this, the asymptotics tell us that if your initial velocity is in either of these two regions, you're going to just asymptotically approach this critical velocity, right? And so that's the main idea here. The qualitative analysis that we do. Well, it tells us that the limit as t goes to infinity of our velocity is going to be this critical velocity, which I'll call v sub c. Right? So whatever velocity corresponds to this purple point here, call that your critical velocity or your fixed velocity. This is what we're going to call v sub c. All right, and what we see here is that your velocity will asymptote back, will asymptote toward this critical velocity. So as t goes to infinity, the limit of the velocity will be this critical velocity, provided that your initial velocity lies in either of these two regions. All right, so one safe thing to say is that if we just cut off this entire half plane, right, so we're only considering negative velocities to begin with, right? So this is our v-axis, it's now only negative. Well, this makes sense for our model, right? Our model was we take an object and we drop it, or possibly throw it down. But we don't necessarily want to incorporate throwing it up in the air and seeing what happens then. So if we just start with an object that's falling, strictly falling, then only considering negative velocities in our coordinate system, which had a negative velocity pointing toward the ground, this is all we would want to consider anyway. So what we can say is that this limit on our velocity will be the critical velocity provided that v of 0 is actually negative. Right? So as long as your initial, less than or equal to 0, I should say. Right? We could just be dropping it as opposed to throwing it. And so as long as your initial velocity is is non-positive, so this thing's not flying up into the air initially, then your limit is going to be your critical velocity. Now, I've called this thing a critical velocity a bunch of times. You probably know it as something else. This is really what we would call the terminal velocity. Right, so this is the general idea behind how a phase plane can really give you some incredibly rich asymptotic behavior, even in the case of a relatively simple thing like an object just falling out of the sky. All right. So that is the main idea for how to do this analysis. Again, you figure out where you graph your derivative with respect to your original variable, and you just see where the thing's positive, where it's negative, draw your arrows to indicate a sense of flow like we had in a direction field, and then use that to tell you your sort of qualitative asymptotic analysis. All right, so this is the idea.